Consider a model catalytic reactor in which a reaction to a given B is being carried out. TA is diffusivity of A and B, C is total concentration of mixture, delta is effective gas film thickness, and XA0 and XB0 are local bulk concentrations of gas. Given this situation, we are asked three questions. First one is, we need to develop an expression for the local rate of conversion from A to B, the rate at which A is disappearing at the catalyst surface is proportional to the concentration of A in the fluid at the interface. So NZ can be written as K1 double dash into Ca. Right here it's given. Now given reaction scheme is 2A giving B. This is catalytic reactor. Here gas A is coming in, and at the surface of sphere which is coated with catalytic material, gas A is converting to B, and simultaneously gas A and gas B are exiting the catalytic reactor. Further, we can write that NBZ is equals to minus half NAZ at any point of Z, because the reaction scheme is 2A gives B. Here we can see that this surface reaction actually occurs, and this is hypothetical stagnant film. So here A enters, it comes with the contact of surface, it reacts to form B, and B exits this film. This is how it goes. We can write NAZ is equals to minus C DAB upon 1 minus half XA into dXA upon dZ. So we can see that it is already in the form of differential equation. So we now make a mass balance on species A over thin slab of thickness delta Z. So this is an element of thickness delta Z. It is an infinitesimally small element, so we can write that dNZ by dZ is equals to 0, assuming that NZ is not changing in that particular thickness. So getting this equation 2, we have to differentiate equation 1 and get this particular equation. So we can write d by dz is equals to 1 by 1 minus half xa into dxa by dz. So we can see here that after differentiating it, we'll get a second order differential equation in xa with respect to z. So we have to integrate it twice to get a real relation between x and z. Integrating it twice, we'll get two constants c1 and c2, for which we'll need two boundary conditions. Fortunately, we have two boundary conditions. At x equals to 0, right here, the xa or the concentration is equals to xa naught, and at z equals to delta, xa is equals to 0. So after substituting value of c1 and c2, we'll get the result as this one. 1 minus half xa is equals to 1 minus half xa naught whole raised to power 1 minus z by delta. Further, we can write NAZ in this particular form. Now jumping to second question is, only using the equation of derived in part A, develop an expression of the local rate of conversion of A to B for two extreme condition, which is diffusion is strongly dominated by reaction and vice versa. So part B, we can write NAZ is equals to K1 double dash Ca, and Ca can be further written as C into XA. So boundary condition 2 becomes, at Z equals to delta, XA is equals to NAZ by K1 double dash C. So to evaluate this, we need to calculate dxa by dz at z equals to 0 and substitute in equation 1, which is this one. So substituting in equation 1, we'll get NAZ is equals to this particular form, and here we can see that in this part it is written as NAZ by K1 double dash into C. So since we know that K1 is reaction is dominating, so K1 is very, very large. So NAZ can further be resolved into NAZ is equals to 2C DAB by delta whole divided by 1 plus DAB into K1 double dash into delta into ln 1 upon 1 minus half xa naught. You can see that this NAZ upon K1 double dash C term is neglected because K1 is very, very large. Now this part is over. Jumping to third part. Third part is, what are the two most important parameters needed to obtain this conversion local conversion rate from A to B. So third part, the two most important parameters needed to obtain the conversion are NaZ and K1 double dash. NaZ is molar flow rate and K1 double dash is reaction constant.